This is a demo of a 1 million point FFT using the AI engines array in a Versal ACAD device. I will use AMD's example design as a reference to port it to a custom platform, build the bare metal application that runs the FFT, and then run it live on the Alpha Data PA100 board. As you can see, makefiles and Tcl scripts are provided to build the example design. And the initial script used to generate the hardware platform is here. Since the design is targeted to the VCK190 evaluation board, we will need to replace the default platform with Alpha Data's platform for the PA100 board. And you will notice that the script uses an extensive platform, and there is no option to include another board file. So we will create a new platform and then generate the image for programming the ACAP. So let's start by sourcing the environment. You'll need Vivado 2024 on works for this. We'll start by opening the example design. And here we need to use the part-based design. That means that we'll be able to substitute with our board file in an easier way. Let's define the part that the PA100 uses. And we'll accept all the default settings. So that's our base hardware to start developing AI engine-based applications for the selected part, but we'll need to particularize the configuration for the PA100 board. So we'll use this project as a skeleton and create another project from scratch with the board file, which will help us populating all the settings that we need automatically. And then we'll get back to this project and incorporate them. We can just write the block diagram Tcl. We'll call it base. Now to get all these required configurations, we'll create another project. And we'll base it on our PA100. Now with this project based in our board file, we'll generate the different IPs with all the configurations that we need, and this will be automatic. So create the block design. And add SIPs IP required for Versal. And then a couple of instances of the NOC. We can copy this over. Well, this will simplify things, as we'll have one that it will be dedicated for routing. And the other two will be dedicated for the DDR controllers. we'll need to select between two bank configurations to match what is implemented in the actual board, and so we'll select with on bank 0 on one AMD and bank 1 on the other AMD. Now let's change the presets of the board file. So all the IOs will be set as required for this application. And let's write the block diagram again. Call it 100. Okay. We'll also need to configure the platform settings, the platform name in this case, and this section appears when we activate the Vivado project option to be an extensive platform, and these fields will be taken by Vitis once the platform is supported to create all the interfaces. Let's call the board 100 alpha. Right, so now we've got all we need to compare both the scripts. Bear in mind that this is the actual definition of the platform name, and we'll copy over to the script itself. Let's open the comparison tool to compare the scripts. We're going to compare the base project that we created for the Versal part, generic, not the VCK190, and the example for the PA100. Now we can see that there are minor differences at the beginning, so we'll copy. This is very important because this property is the one that defines the board file. And crucially, now the SIP settings, we need to get all the PMC and PS configurations, so all the peripherals need to be copied over. What we're gonna do is to select what we don't want to be in this project, which are, as I said, all the peripherals and all the PMC settings. Sometimes they are intertwined, so we just need to remove additional peripherals. And then let's just take the whole PMC and PS configurations block. Now we get also the presets for the board file. Additionally, we'll want to configure the AMD to be set as per board file definition, which makes things much easier. So let's try and find the AMD here. And the first one we see is this one. It doesn't matter in principle which one we choose to add the memory controllers, because they are both DDR memory controllers. So The only thing to take into account here is like the AMD's example design has LPDDR memory, whereas the PA100 has 2 banks of DDR4 memory. Actually, this is a mistake because, as you saw earlier in the video, we saw 3 different instances of the AXI-NOC IP. One of them was dedicated for routing, which in this case is this one, SIPS-NOC, and the other ones are dedicated for the memory controllers. The first one appearing here is DDR4, so we'll add these lines. This is the configuration for the bank 1, as we are using board files, so we'll need to find the next one. And as you might be expecting, well, in this case it's LPDDR. The names doesn't actually matter, but what it matters is how the instance of the AXI node is configured. So let's remove the LPDDR4, which is the other AXI node that we saw in the base example, and then as I said, you'll just need to change which bank you are addressing here. The remaining configurations, we'll keep them because these are actually the ones that maps to the system memory map in Versal, and these don't change. This one needs deleted because we don't have LPDDR anymore. Now, if we go to the beginning of where the block diagram is created, we realize that we have a number of port definitions, and because we change the type of memory, we'll need to change the interface. So we'll just rename the ports to a new DDR port instead of the LPDDR, and the controller itself, I mean the interface definition in Vivado needs to match that type of memory. Other than that, it's just giving a different name and wire it up later in the script. So let's check that we don't have any remaining connections that are hanging this. And another important setting that needs to be changed here is the clock reference for the DDR4. So on the PA100 is 300 megahertz, and we'll use that in both banks. Now, another thing that will be missing here is, as you might remember, what we did with the platform name. So if we get back to the TCL command that we generated by using the UE to name the platform, we'll just be able to copy it over and replace it here. Right. And that's it. And let's not forget the connections to the ports that we created, which are down here as well. So let's duplicate the DDR4 connection. This one is called LPDDR4. Even if it's not, but it's just the AXI NOC label, and that's the port, the physical port, and this is the actual label of the port, the external port, whereas this is just the name of the net, which is irrelevant. So let's just remove the other ones, and so that's it, really. Let's try and run this and see if that creates the same block diagram with the correct settings.
Let's save the comparison. And now let's run it again to see everything's fine.
Let's run the 1 million point FFT on the custom board with the Versal ACAP device. The board is ready with the micro SD card with the binaries we just generated. So in order to run the 1 million point FFT, we'll need to boot from the micro SD card, and then the example will run automatically. And for that, I'll use this terminal here to open the serial port where the board is connected to. And then we'll be able to see the board booting. Now, in another terminal, we'll open the Vitis console and connect to the board. We have it connected with the JTAG cable, and then I just selected the Versal device, and I'm going to assert a system reset, which is equivalent to a PORB signal assertion. We can see on the terminal that the Versal bootloader is booting from the SD card. Next, the PS program runs the test showing the statistics of the cycles taken for processing and its latency with no mismatches compared to the expected output. Finally, we are presented with a summary of the 64 kernels running in parallel for the 1 million point FFT with input data of 32 bits floating point. Each core runs at 479.8 megasamples per second, achieving an overall data throughput of 30.7 gigasamples per second. An impressive figure. So that's it for the demo. And to learn more about the host application details and the FFT implementation, you can visit the link below. Thank you for watching.